see. Today we're going to be walking through DNA replication. Alrighty, so let's go ahead and start by drawing our strands of DNA. So this will probably look a little bit familiar. This is a very strange setup. If only you guys could see. So I'm not an artist, as most people know. So we have our 5' to 3' end. And then on this other strand, we have 5' here, 3' here. Alrighty. So keep in mind, this is in prokaryotes. So where does this happen? The cytoplasm. So within our DNA replication, we'll have our base pairs, right? Let's use these guys. And I don't want to run out of room. Okay, let's do our complementary. And remember, this is DNA, so we'll still have we'll still have thymine and not uracil quite yet. We'll see when uracil does come into play, though. All right, so we have our strand, and you'll notice that it's not its normal double helix, right? Usually DNA will look something like this. That's not the easiest way for me to draw a double helix. So usually DNA will look something like this, where the base pairs do have that bond. Now remember, I have, here, let's see a little better. I have 2 hydrogen bonds there, and then between, guanine and cytosol, I'll have 3. All right, so now to actually get started with our replication. First up, we're going to unwind. Have a cocktail by the beach and unwind. I'll just use a normal highlighter for this one. So, our friend that helps us unwind, right here, it's our friend helicase. Our friend helicase is going to help us unwind so that we can get to work. It's important to keep in mind that helicase is going to move in this direction, and so is our direction of replication. There we go. We have another friend in here. It's like, I like to call this guy, I'll put him right here. I hope this shows up. There we go. This is going to be our gyrase. Let me put his name tag on. Now the relationship that these two guys have is that helicase loves to unwind, but for some reason, an hour into unwinding, helicase all of a sudden remembers all of its problems and gets all tense and coils up. So what gyrase, the wonderful friend it is, what gyrase does is it relieves supercoiling. That's what our friend gyrase does. Okay. Oops. Noises, sorry. Alrighty, so once we have our first friends in the motion, they are going to make everything nice and primed up for primase. I'll get in here with green. So primase is going to start towards the 3' end because it's going to replicate 5' to 3'. So here, I'll show you guys. This will be primase. This is a terrible marker, but we'll go with it. I have another green highlighter, so we'll work on it. So primase, that's these little triangles. Primase is going to start us off. Primase moves from 5' to 3' on its own strand. When you hear that 5', how it replicates, it's going to replicate 5' to 3'. But you have to put it in context of the other strand as well. It moves from the original strand 3' to 5' in order to replicate 5' to 3'. I know it's very backwards, but just bear with it. You'll be okay, I promise. I'll use a green. I have lots of pens, if you could not tell. This is a Christmas one, I know, but it has a bunch of colors on it, so I love to use it. So for this one, I'll use a green to show you that we're now going to be making our leading and lagging strands. Sorry, I got carried away with the green. And now there's a big difference here. What do we see? There's no more thymine. We're in uracil, so that must mean that we're now coding for RNA. No more DNA here. We're coding for RNA. Now, this just doesn't happen on one side, right? It's going to happen on this side, too. But what happens when we reach this point? There's nowhere else to go. This is, if you'll bear with me, this is a tumbleweed. This is nothingness. So what happens? Well, this is what we call our Okazaki. I believe that's how you spell it. Okazaki fragments. If I don't, please correct me. But we see how this is our leading. We're going to call this one our lagging. I mean, you know, the first thing that comes to my mind in terms of lagging, now I don't play video games very regularly, but I do know that whenever you're in a game and you lag, you know, your game gets all choppy, it kind of jumps around, and it's all over the place. So that's how I remember lagging, is that it's going to be several fragments of an actual picture. So yes. Now our primase is going to also keep in mind, it could be interchangeably called our RNA primer. Just a small note. Let's see. I believe that's all that primase really does. It really just starts us off in our RNA journey. Alrighty. So now, I know it's very backwards. You would think that DNA polymerase 1 should be the first one to show up. However, that's not quite the case. So here, my marker's a little faded, but here in blue is going to be our DP3. Like a little key off to the side here. This is going to be our DP3. DNA polymerase 3. Now, DP3 adds on DNA to growing strand. This growing strand was started by primase, which was unwound by helicase and kept unsupercoiled by gyrase. So we have lots of players in action here. So let's break it down. DNA. What are our base pairs? A, G, C, and T. Yes. So if you were given a strand, and let's say this section and then this section, it was A, C, C, G, U, A, and this section was, you know, the same strand, so they're not going to be complementary. it's going to go G, G, A, T, T. If I were to ask you what was created by primase and what was created by DP3, you should be able to tell me, right? Because this is RNA here, and this is DNA on this side, but they're still part of the same strand and they're not complementary. So this would have been made by primase, and this would have been made by DP3. All right, back to our story. So here, our DP3 starts and continues, but this time it adds DNA. G, A, T here, and I finished this in RNA, so I'll just continue here. So C, A, T. Alrighty. So now we have a continuation, but this stops here. So now we have our leading and lagging strands started. So leading, by its nature, only needs primase once because it starts here and it can keep going. But lagging needs a little extra help. Lagging, we're going to have to start over later on. But for now, when we focus on this picture, we'll talk about what happens here and then when it starts over. I'll have to draw a whole new thing for that, but we'll figure it out. Okay, what's the next color? I like red. Alrighty. So obviously, we can't have this exist anymore, right? That can't exist in our actual proteins, right? We can't code for anything this way because once this gets fed through a ribosome, they're not going to know what's happening. So, we have DP1. Comes in and it cuts out the RNA primer and adds DNA nucleotides in its place. Alrighty. So I'm gonna yank this guy out and replace it, right? This guy's gonna get all kinds of replaced. So soak this in. I'm probably gonna redraw it in a second here and show you what's kind of happening. I'll do a small version in this corner first, right? So just to color code it for you, this is what's happening, right? We have what was initially made by DP3, right? But you see how it was green here? See how it's green here? We're going to replace that with a red. Just to show you that it's continuing in this direction and this one is going this way. Alrighty. So now at this point we're in terms of DNA. So our base pairs are going to be these. Next, our wonderful friend ligase comes in to take these out. These will be no more. These little weird jumps from one to another, they're fragmented, right? So our ligase, our glue, Elmer's, is going to come in and glue these together. So let me, on the other side here, glue. Sorry. On the other side here, let me do this. So now when that glue came in, we're going to look a little more seamless. Now let's remember that this is going to be our direction of replication. Label our primes here. Get our base pairs back. try to do this quickly. All right, DNA, right? So now that I have like 3 different red pens, but anyways. So in this direction, we have our base pairs, right? We have A, and in this direction, can't quite fit all of them together, but let's do that and then that. Okay. So remember what I said about this thread, right? This is the lagging. Up here and leading down here. Now this one is going to go very quickly, very fast. It's going to get all the way through, right? This one has those Okazaki fragments. Okay. All right. And this is only after that ligase has come through and sealed the DNA sugar phosphate backbone together. Alrighty. So if we were to just look at this, let me do this in black. If we were to just take this top part here and look at it on a more linear aspect, so what's essentially going to happen, right, our helicase and gyrase already came through. So now we're going to start the show with primase. So primase, let's say it's only unwound to here. Primase is only really started there. Primase comes in, and it works a little bit. I'll just do this. It works a little bit. Now our DP3 knows where to start, comes in, starts, runs out of room. Where do I go from here? Well, we have to go through that whole process of, let's see, we have to go through the whole process of, what color did I do first? I did red, okay. I also did red for ligase, I guess. We have to do that whole process of replacing this with DNA so that it all looks like this, right? That's our DP1 coming in. And then we have to also show that ligase comes in and doesn't give that weird bump. So now this is all DNA, but at this point, now what? Well, primase has to start all the way down here again at a different spot and prime us up. DP3 now knows where to go. It'll start and keep going in this direction. Sorry, I drew it the other way. It'll keep going until it hits the wall. Now, now DP1 will come in and join its friend DP3. Well, now, not only do we need glue here, but we need glue here. So now ligase will come through and, I'll draw it from the other way, connect these 2 strands. And that'll keep repeating itself over and over and over. So this is kind of our step 1, I guess, step 2, and then 3. And this is why those are the Okazaki fragments. I hope this makes sense. If you have any questions, let me know. If there are any questions specific to any of the enzymes needed to perform
DNA replication, let me know. Any questions about specifically prokaryotic DNA replication, let me know. But yes, just a final note, remember that DNA is, or a chromosome in a prokaryote is circular, and that our strand, it's going to look a little weird because there's going to be just this spot that kind of open up. And it's going to keep moving along like a zipper until finally it's going to look a little bit bigger. There are two strands, just like that. This is the point where helicase and primase are. If we assume that this is going to be 5' to 3' up top, and then 3' to 5' down here. Let me know if you have any questions. I would encourage you to draw this out for yourself. And if you need anything, just let me know. Alrighty. I hope you guys are doing well in this chapter, and I will talk to you soon. I hope you guys saw half of what I just wrote up here.